Let's discuss a question from thermodynamics. This is from applied thermodynamics Rankine cycle. So let's plot Rankine cycle in a TS diagram. Well, it's a something like a bell curve where constant pressure lines look like this. Inside the dome it is constant, pressure is constant, and the temperature is constant. After that it just varies like this. So now in a Rankine cycle, what happens if let's start from the pump? Well, the pressure increases. Now it goes to the boiler where the action starts. So let me call this as the pump inlet as 1, pump outlet as 2. Then it goes to the boiler, and then in the boiler well, energy is supplied by means of combustion, and the enthalpy increases. So at point 3 it goes to the turbine where there is a work done and the enthalpy decreases. Okay, a constant in an ideal turbine it will be a constant entropy, isentropy process will go on, and 4 to 1 it's again back to the condenser where heat is rejected to the outside, okay, atmosphere. So this is the process. At 4 it is given that exit of the turbine there is some dryness fraction, so at 4 we have just drawn this. So basically we need to find out the thermocycle, but before that, so what we will do is we'll just find out the enthalpies at each of the 4 points, because that will be useful. So H3 is already given that this is 3 MPa, and let me just and this is 75 kPa. So already the HF everything is given. Now at point 3 where it enters the steam turbine, the temperature is also given. This is 350 degrees Celsius. So H3 is basically given, the enthalpy it is 3116.1 kilojoules. So all these are kilojoules per kg values. H3 is given. Now H4 can be found out because it's in the saturated domain, so HF into X into HFG. Now dryness fraction is already given, so HF is basically this value, HF at 75 kPa, so it's already given 384.44 plus dryness fraction is 0.8861. HFG is HG minus HF, so that is HG is, or the HFG is directly given, so you need not, 22780. So this value H4 comes out to be 2403 if we calculate kilojoules per kg. So we got H4 also. Okay, now H1 is nothing but HF, because that's where the pump enters, and that is 384.44 kilojoules per kg. So we already have HF. Now H2 is basically H1 plus work done by the pump. I mean, if you apply a steady state flow equation between 1 and 2, so whatever the work is done by the pump, it's in an isentropic process, so there is no heat loss. So work done by the pump, it will be increasing the enthalpy. H1 is already, we know, 384.44 plus work done by the pump is 3 joules, so it is 387.44 kilojoules per kg. So we got H2, we got H1. So efficiency is basically work done by the turbine, the net work done, that is work done minus work done by the turbine minus work done by the pump. Okay, this is the net work done by the heat input, and heat input, so this is H3 minus H, so this is H3 minus H4 is the work done by the turbine, minus work done by the pump is already given as 3 kilojoules. Heat input is H3 minus H2. Okay, so we know, that's the reason why we found out enthalpy first, because we will be knowing everything. So 316.1 minus H4, that is 2403, minus 3 by H3 minus H2, that is the heat input in the boiler, enthalpy change that occurs in the boiler. 3116 minus 1 plus 2 minus H2. H2 is basically your 387.44. So if I calculate this comes out about 26%, 0.26, that is 26%. So this is a standard thing. So remember that Rankine cycle, Brayton cycle and refrigeration, these are 3 cycles out of which there you can expect at least a 1-2 mark question, if not a common data question. Okay, so the answer is 26%. Thank you.